The National Electrical Code, or NEC, addresses the installation requirements for conductors without an outer covering, specifically types used to RHH and RHW2. According to NEC 336.109, these conductors are generally prohibited from use in exposed locations unless specific conditions outlined in 336.109 through E are met. When these conductors are used as branch circuits or feeders and not run in raceways or concealed spaces, they must adhere to the installation guidelines specified in 336.109 done 33. One crucial aspect of these guidelines, as stated in NEC 336.109 D2, is the protection of conductors installed in accessible unfinished basements, attics, or roof spaces. Such conductors must be safeguarded by substantial guard strips or other equivalent means. Now, considering a scenario where type used to RHH or RHW2 conductors, specifically a 4-conductor cable with number 2 for the phase conductors, number 2 for the neutral, and number 4 for the equipment grounding conductor, are run without conduit from a 200 amps main panel in a basement across the bottom of joists up into an attic, and then down into a 100 amp subpanel. Certain NEC requirements come into play. Given that the conductors are being used as branch circuits or feeders and are not run in raceways or concealed spaces, and that they are installed in an attic and basement, which are considered accessible unfinished spaces, the installation must comply with NEC 336.109 D2. This means that the conductors must be protected by substantial guard strips or other approved means. Regarding the question of whether conduit is required where the conductors enter the panel, the answer is yes. The NEC mandates that the conductors be protected by substantial guard strips or other means where they enter the panel, which is typically achieved by using conduit. Furthermore, the question of whether conduit is required after the conductors pass under a trailer also necessitates a yes answer. Since the conductors are being used as branch circuits or feeders under a trailer, which is not a concealed space, they must be run in conduit according to NEC 336.109 done. To further clarify the requirements for using conductors without an outer covering, let's delve deeper into specific NEC sections and practical applications. We'll explore the conditions under which these conductors can be used in exposed locations, the types of protection required in accessible unfinished spaces, and the proper methods for transitioning between different wiring methods. First, let's examine NEC 336.109 in more detail. This section outlines specific exceptions to the general rule that conductors without an outer covering should not be used in exposed locations. These exceptions, detailed in 336.109 through E, include situations such as direct burial applications, installations in agricultural buildings, and use as service entrance conductors. However, these exceptions often come with specific requirements regarding conductor type, burial depth, and protection against physical damage. Next, let's focus on NEC 336.109D, which is particularly relevant to the scenario involving basements, attics, and trailers. This section emphasizes the importance of protecting conductors used as branch circuits or feeders when they are not installed in raceways or concealed spaces. The code provides 3 options for compliance, outlined in 336.109 done through 3. The first option, 336.109 done, requires the conductors to be run in conduit when installed in locations subject to physical damage. This is particularly applicable to the portion of the installation under the trailer, where the conductors are vulnerable to damage from vehicles, debris, or other external factors. The second option, 336.109 D2, applies to conductors installed in accessible unfinished basements, attics, or roof spaces. In these locations, the conductors must be protected by substantial guard strips or other means. This could involve installing wooden or metal strips along the joists to prevent the conductors from being easily damaged, or using cable trays or other support systems to keep the conductors out of harm's way. The third option, 336.109 D3, allows for the use of specific types of cable, such as type MC cable, which has a metallic sheath that provides inherent protection against physical damage. However, This option may not be suitable for all applications due to cost or other considerations. In practical terms, implementing these requirements involves careful planning and execution. Firstly, assess the specific conditions of the installation to determine the most appropriate method of protection. Consider factors such as the likelihood of physical damage, the presence of moisture or corrosive substances, and the accessibility of the conductors for maintenance or repair. Secondly, select the appropriate materials and equipment. If conduit is required, choose a type that is suitable for the environment and the type of conductors being used. Common options include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and flexible metal conduit. If guard strips are used, ensure that they are made of durable materials and are securely fastened to the building structure. Thirdly, install the conductors of protection systems according to best practices. This includes properly supporting the conductors, avoiding sharp bends or kinks, and ensuring that all connections are tight and secure. When transitioning between different wiring methods, such as from conduit to open wiring, use appropriate fittings and connectors to maintain electrical continuity and prevent moisture from entering the system. In addition to these specific requirements, it's important to consider general wiring practices and safety precautions. Always de-energize the circuit before working on any electrical equipment. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow the manufacturer's instructions for all materials and equipment. And if you're not comfortable working with electricity, hire a qualified electrician to perform the work. To further illustrate the application of these principles, let's consider a few examples. Imagine a scenario where conductors are being run across the bottom of floor joists in an unfinished basement. In this case, the conductors are exposed to potential damage from foot traffic, stored items, or plumbing leaks. To comply with NEC 336.10 D2, the conductors could be protected by installing wooden guard strips along the joists, providing a physical barrier against damage. Alternatively, the conductors could be run in conduit to provide a more robust level of protection. In another scenario, conductors are being run through an attic space that is used for storage. In this case, the conductors are at risk of being damaged by boxes, furniture, or other items stored in the attic. To comply with the NEC, the conductors could be supported on cable trays or secured to the rafters with cable ties, keeping them out of the way of stored items. Additionally, guard strips could be installed in the areas where the conductors are particularly vulnerable to damage. Finally, consider the scenario where conductors are being run under a trailer. In this case, the conductors are exposed to potential damage from road debris, weather conditions, and physical impact. To comply with NEC 336.10 done, the conductors must be run in conduit to provide adequate protection. The conduit should be securely fastened to the underside of the trailer and should be made of a material that is resistant to corrosion and physical damage. In summary, the installation of conductors without an outer covering requires careful attention to detail and compliance with the NEC. By understanding the specific requirements for different locations and applications, and by implementing appropriate protection measures, it's possible to ensure a safe and reliable electrical system. Remember to always consult the latest edition of the NEC and to seek the advice of a qualified electrician if you have any questions or concerns. Now let's expand on the topic of selecting the right type of conduit for different applications. The NEC recognizes several types of conduit, each with its own characteristics and advantages. Choosing the appropriate type of conduit is crucial for ensuring the long-term durability and safety of the electrical system. Firstly, rigid metal conduit, or RMC, is a heavy-duty type of conduit that is typically made of steel or aluminum. RMC provides excellent protection against physical damage and is suitable for both indoor and outdoor applications. It is often used in locations where the conduit is exposed to severe weather conditions, heavy traffic, or potential impact. Secondly, intermediate metal conduit, or IMC, is a lighter weight version of RMC. IMC offers similar levels of protection to RMC but is easier to bend and install. It is commonly used in commercial and industrial applications where a high level of protection is required but weight is a concern. Thirdly, electrical metallic tubing, or EMT, is a thin-walled conduit that is typically made of steel or aluminum. EMT is lightweight and easy to bend, making it a popular choice for indoor applications. However, EMT is not as strong as RMC or IMC and is not suitable for use in locations where it is exposed to severe physical damage. Fourthly, flexible metal conduit, or FMC, is a flexible type of conduit that is typically made of steel or aluminum. FMC is used in applications where the conduit needs to be bent or routed around obstacles. It is commonly used to connect equipment to electrical boxes or to run wiring in tight spaces. Fifthly, liquid-tight flexible metal conduit, or LFMC, is a type of flexible conduit that is designed to be watertight. LFMC is used in applications where the conduit is exposed to moisture or wet conditions. It is commonly used to connect equipment in outdoor locations or in areas where there is a risk of water damage. In addition to these common types of conduit, there are also several specialty types of conduit available, such as rigid non-metallic conduit, or RNC, which is made of plastic and is resistant to corrosion, and electrical non-metallic tubing, or ENT, which is a flexible non-metallic conduit that is used in concealed locations. When selecting the appropriate type of conduit, consider the following factors. Firstly, the environment in which the conduit will be installed. Will the conduit be exposed to moisture, chemicals, or extreme temperatures? Secondly, the level of physical protection required. Will the conduit be exposed to heavy traffic, potential impact, or other hazards? Thirdly, the ease of installation. Is the conduit easy to bend and route? Fourthly, the cost. How does the cost of the conduit compare to other options? By carefully considering these factors, you can select the type of conduit that is best suited for your specific application. Remember to always follow the manufacturer's instructions and the requirements of the NEC when installing conduit. This will help to ensure a safe and reliable electrical system. Also, it is important to note that the NEC contains specific requirements for the support and fastening of conduit. These requirements are designed to prevent the conduit from sagging, pulling away from connections, or otherwise becoming damaged. Conduit must be supported at regular intervals, typically every few feet, using appropriate clamps, straps, or hangers. The supports must be securely fastened to the building structure and must be able to withstand the weight of the conduit and the conductors it contains. In addition to supporting the conduit, it is also important to properly ground the conduit system. Grounding helps to protect against electrical shock and to prevent the buildup of static electricity. Metal conduit systems are typically grounded by connecting them to a grounding electrode conductor, which is a wire that is connected to a grounding rod or other grounding electrode. Non-metallic conduit systems do not require grounding, but they must be installed with a grounding conductor that is run inside the conduit. Finally, it is important to inspect the conduit system regularly to ensure that it is in good condition. Look for signs of damage, such as cracks, dents, or corrosion. Repair any damage promptly to prevent electrical hazards. By following these guidelines, you can ensure that your conduit system is safe, reliable, and in compliance with the NEC. Let's now talk about grounding conductors. Grounding conductors, also known as equipment grounding conductors, play a vital role in electrical safety. Their primary function is to provide a low impedance path for fault current to return to the source, which helps to quickly trip a circuit breaker or fuse and prevent electrical shock. The NEC specifies the requirements for grounding conductors in Article 250. According to the NEC, all metal enclosures, such as electrical boxes, cabinets, and equipment frames, must be grounded. This includes the metal conduit that we discussed earlier. The grounding conductor must be sized according to the size of the overcurrent protection device protecting the circuit. The larger the overcurrent protection device, the larger the grounding conductor must be. The grounding conductor must be connected to the metal enclosure in a manner that ensures a good electrical connection. This can be achieved by using grounding screws, lugs, or other approved methods. The grounding conductor must be run with the circuit conductors. This means that the grounding conductor must be installed in the same raceway or cable as the hot and neutral wires. The grounding conductor must be continuous and unbroken. This means that the grounding conductor cannot be spliced or cut. If the grounding conductor is damaged, it must be replaced in its entirety. In addition to these general requirements, the NEC also contains specific requirements for grounding different types of equipment. For example, the NEC contains specific requirements for grounding swimming pools, spas, and hot tubs. The NEC also contains specific requirements for grounding sensitive electronic equipment. When installing grounding conductors, it is important to follow the requirements of the NEC carefully. This will help to ensure that the electrical system is safe and reliable. Now let's talk about overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Overloads occur when the current in a circuit exceeds the rated capacity of the wires or equipment. Short circuits occur when there is a direct connection between two or more conductors that are normally insulated from each other. Overcurrent protection devices work by interrupting the flow of current when an overload or short circuit occurs. Circuit breakers are reusable devices that trip when an overcurrent occurs. Fuses are one-time devices that melt and break the circuit when an overcurrent occurs. The NEC specifies the requirements for overcurrent protection in Article 240. According to the NEC, all electrical circuits must be protected by overcurrent protection devices. The overcurrent protection device must be sized according to the ampacity of the wires and equipment being protected. The ampacity of a wire is the maximum amount of current that the wire can safely carry. The ampacity of a wire is determined by its size, material, and insulation type. The overcurrent protection device must be installed in a readily accessible location. The overcurrent protection device must be marked with its ampacity rating. When selecting overcurrent protection devices, it is important to consider the following factors. Firstly, the ampacity of the wires and equipment being protected. Secondly, the type of circuit being protected. Thirdly, the interrupting rating of the overcurrent protection device. The interrupting rating is the maximum amount of current that the overcurrent protection device can safely interrupt. Fourthly, the voltage rating of the overcurrent protection device. The voltage rating is the maximum voltage that the overcurrent protection device can safely handle. By carefully considering these factors, you can select the overcurrent protection devices that are best suited for your specific application. It's important to remember that electrical work can be dangerous. If you are not comfortable working with electricity, hire a qualified electrician to perform the work. Always de-energize the circuit before working on any electrical equipment. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow the manufacturer's instructions for all materials and equipment. And if you have any questions, consult the NEC or a qualified electrician.